Hi there and welcome to Simulation-Driven Product Development with Freeform Fabrication. My name is Eric Miller. I'm one of the owners and a principal here at PADT. And today we're going to talk about how we can combine two of our favorite things here at PADT, additive manufacturing and simulation, to create parts that really we couldn't design or manufacture in any other way before. And these two technologies work very, very well together. And we'll talk about how we've learned a lot about it and some things that you need to know if you're going to get into this whole area and take advantage of the cool things you can do with it. So let's start with a little bit of an introduction. A little bit about our company, Phoenix Analysis and Design Technologies, or better known as PADT. We're a products and services company for physical product development. If you make a physical product, we either can sell you a tool to do it better, or we can provide you a service to help you make it a better product. We've been an ANSYS channel partner for a very long time, and we sell in the Southwest: Arizona, New Mexico, Colorado, Utah, Nevada, and Southern California. We do three things here at PADT. We do simulation, product development, where we design and help people test and manufacture their products. And then we also do 3D printing or additive manufacturing. Our headquarters is here in Tempe, Arizona, where I'm recording this from. But we also have offices in Albuquerque, Denver, Salt Lake City, and in Los Angeles, our newest one. And you can find out a lot more about us, of course, on the web at padtinc.com. A little bit about me, other than the fact that I will stumble my way through this and back up every once in a while when I forget what I was talking about. I'm one of the co-founders and owners of PADT here at PADT. Been here for 22 years since we started the company. I'm a mechanical engineer by trade. And I graduated in '86 from UC Berkeley with a mechanical engineering degree, as you would imagine. And I spent most of my technical career doing finite element analysis, software development, and design, really solid modeling and advanced complex geometry modeling using CAD tools, and kind of combining those three together quite a bit through my career. Other responsibilities here, besides being one of the owners, is I do marketing. The HR manager, or not really the manager, the HR manager reports to me, and the operations manager reports to me as well. IT actually is in there as another area that reports up to me. I've been using ANSYS for 30 years. It's been a very long time. Using CAD for 32 years, and I've been using 3D printing in addition for 25 years, I think. I'm not quite sure when that first part was I had made when I had a job in a large corporation, but I think it's been about 25 years. And you can get hold of me if you have any questions or comments or talk about anything else at eric.miller@padtinc.com. And it is best to email me. I don't necessarily, I'm not usually around to answer the phone. So what we're going to talk about here is combining these two things. The idea of unconstrained geometry, shape optimization. So I can use these simulation tools to optimize the shape of my part without very many constraints. And now I've got this new additive manufacturing. I can do unconstrained manufacturing. So I can make any shape that I can come up with. These two things kind of fit together perfectly, and have created a whole new world for us doing design of parts. So we're going to start off by talking about what freeform fabrication means to product development. So we're going to talk about how you make these parts. Then we're going to talk about topological optimization as a way to drive the design using simulation to come up with these shapes to optimize them. And this is not a fairly technical. It's pretty high level, kind of fuzzy look at things, not too detailed in the technology. And you can always reach out to us to get the details if you want. We'll talk about some of the near-term plans from ANSYS Inc. We'll take a look at the future, where things are headed, and that's pretty much it. So let's jump right into it and talk about this whole idea of simulation-driven freeform design. So what is freeform fabrication? Before we talk about what freeform really means, we need to talk about some official terms used in advanced manufacturing. And I'll use the wrong term when I'm talking all the time. Apologize for that. But here are the official terms that we should be using. So freeform fabrication is any manufacturing method where a tooling and process do not constrain the shape of the geometry. I can make whatever shape I want. It's almost kind of an ideal. It's almost a stretch goal to have no constraints. Additive manufacturing is where you create the final shape by adding material. So you're building material up. Traditionally, or not to say traditionally, but most commonly today on layers. You're building material up on layers. And in most cases, Additive manufacturing is a subset of freeform fabrication, and it's the most widely used approach for freeform fabrication, where you're adding stuff together. There's machines out there that combine removing material and molding material and adding material, and then there's freeform tools that create molds kind of on the fly. So there's other ways to do freeform, but the one we see the most is the additive process. Traditional manufacturing, subtractive, that's machining. That's where you remove things over time. Casting is where you make a liquid of some kind and you put it into some sort of a tool and it solidifies into the shape you want. And then forming is where you distort the material into the shape you want. So that could be extruding, that could be uh, metal forming, it could be forging, it could be metal bending. These are all different forms of forming. And then I want to bring up the term 3D printing, and I'll use it wrong because it's kind of become a generic term, but it's low-cost desktop additive manufacturing is the official definition. When you talk about 3D printing, this is consumer level or desktop level additive manufacturing. So what freeform fabrication does is it gives us freedom. We'll be using that free word a lot. It removes constraints of traditional manufacturing. The constraints that it removes are I don't have to worry about how I can get my tool in if I'm machining something. I don't have to worry about the size of the tool, like I need a fillet of a certain size. I have to make sure my tool is smaller than that. I don't have to worry about draft when I'm molding or casting. I don't have to worry about how I'm going to get the part out. Also in casting, you've got problems with drift and shrinkage. These are things you really have to deal with and very complicated. And also, we're seeing more and more is we can solve assembly problems. So the only way to make a part is in maybe multiple pieces, and then I got to weld or solder them together. I don't have to do that. Sometimes with additive, I can just build it as one piece. So what freeform manufacturing gives us is the shape we want, and even more importantly, often is internal features that I have to either do an assembly to get at, or I have to figure out how I'm going to get a tool in there, or maybe I even can't get a tool in there. So of course it's not a free lunch. It's not the perfect technology. There's limitations in the process. It is generally speaking a layered process, and it generally does not create a smooth surface. You have to smooth the surface afterwards. In most of the cases, the material is not orthotropic, and it's cast properties at best, and often worse properties than cast. Uh, there's supports that you have to design in, so the part supports itself if it's not made in a powder bed, and if it is made in a powder bed, you still have to use supports to kind of hold stuff in place. The other thing that many of these processes involve heating of one kind or another, so thermal warping is an issue. Residuals are kind of another thing that gets in there. Um, and then after you've made the part, you got to be able to remove the powder that you built it in or the supports that you built it in. The other limitation is the expense. It can be much more expensive than traditional methods, and there's always a trade-off there. And it's also not necessarily the best technology for high volume manufacturing. If you're doing low volume or custom parts, it's really nice, but if you're going to make a million of them, it'd be hard pressed to show that additive is the way to go. I mean, maybe the only time that you're going to use that is when there's no other way to make the part. So let's move on to removing manufacturing constraints. So when we use freeform fabrication, we go ahead and take away these constraints we've had to deal with. Even though you're using optimization, you still have to worry about the fact that there are some constraints in the process. But additive manufacturing creates a much wider space for geometry variation. So my design space is now much less constrained. Keep on warning people there's still constraints. I keep bringing this up because people will design parts that can't even be made with additive manufacturing. So you got to know the capabilities of the process. You got to know it's just like traditional. You shouldn't be designing a part that's going to be injection molded unless you understand injection molding. Don't design a part that's going to be made with additive manufacturing unless you understand the process you're going to use. But in the end, we've got a lot fewer constraints, so that's why we're very excited about this technology. The other thing that we're excited about is it adds new options. One of the cool things that it adds is the ability to do composite structures. There's a lot of work going on in making machines that will mix materials as you build. Stratasys is way ahead on this. I didn't mention in the introduction, PADT is a Stratasys reseller as well. So we sell the full line of Stratasys equipment, including their digital material machines. So we can build parts that are hard and soft, that have different materials. They basically have multiple print heads, and each print head can put out a different material. So we can mix them on the fly. We're also seeing people look at how to add fibers and nanoparticles into their material in order to get kind of a composite behavior. The other thing we're seeing more and more of is cells. So this is where we go ahead and we break these solids up into non-solid geometry. And we can get whatever shape we want, whatever stiffness we want using that. It's really promising. I mean, think honeybee combs. Think hexacores. I mean, in aerospace, we've used these flat hex cores for many, many, many years. Now I can have a freeform shape with these cores in them. So you get a lot of weight reduction. You can have the density and stiffness where you want it, and I'll talk about that a lot. And the other thing that we're starting to see, especially in the medical space, is I can get kind of an organic behavior where I get density and stiffness and material where I want using these cells, kind of like bone and cellular structures in trees and plants. So very exciting stuff. So what are the key features you should be aware of when you look at additive manufacturing? So you decided you're going to make a part using additive. It's going to be a tooling or a production part. What are the features I need to be aware of? Well, I'm going to break it into two sections, one for plastics or polymers and the other for metal. So with polymers, you have to deal with the fact that it's layered. Also that it's not isotropic. It's not fully dense. It's something that you have to really be aware of because it can cause fatigue problems and durability problems. We have a limited set of materials. You know, there's thousands of polymers out there. We've got maybe dozens available on 3D printing, and they're not necessarily identical to traditional polymers. So you got to be aware of that. And there's five major technologies you should be aware of, and we're not going to do a course on 3D printing. I'm going to assume that most engineers are pretty aware of this. If you're not, take a look at our website. We've got a lot of details on this stuff, but you've got your stereolithography, your selective laser sintering, your fused deposition modeling, polyjet, and binding. People may not be as familiar with these two. Polyjet is where you use a printjet inkhead to put out a material that hardens when ultraviolet light hits it, same as a stereolithography, but you're putting down little droplets, and that's where we can mix the different material and get different behavior. And then binding is where I also use an inkjet printhead, or maybe an extrusion head like fused deposition modeling, but I'm putting out a glue, basically, some sort of a binding agent, and or I'm heating up a coating to get the parts to bind together, and that can make really cool parts like ceramics. This is one of the ways to make green parts for ceramics. The other thing to be aware of is that you have to deal with supports with polymers or powders. If you're going to use a powder, not only have to design them into your part or use software that creates the supports, but you also have to figure out how you're going to get them out of there. So let's move over to metal. So it's also layered. It's not isotropic, but it can be fully dense. So using some of the melting processes, we can get there. And it's a pretty full range of your powder metals. If maybe your machine manufacturer has not figured out all the parameters, so you got to do it yourself. But if you've got a powder metal, you can pretty much use these technologies to build a part with it. We can achieve, if you do it right, cast properties, which is really exciting. You do have to deal with residual stresses. This is the big gotcha, the thing you have to really, really be careful about. And you have to do a lot of post-processing to get rid of these. There's three major technologies to be aware of. Laser melting is the dominant one. That's where we use a laser to melt a powder bed. And this is what makes the fully dense cast property parts. There's sintering, where we don't quite get as hot, but we put a coating on the metal and of plastic usually, and that causes the parts to stick together, or maybe even get hot enough to where the metal actually sticks together. But it's not, again, it's not going to melt. It's not going to be fully dense. And then we can also use the binding process to make green parts. So we can glue the material together and go from there. And I mentioned ceramics very briefly. It's kind of a newer area. It basically uses binding and behaves a lot like a polymer / metal hybrid there. And we still have to make a green part, and we still have to fire it and infiltrate it afterwards, just like metal when we use a binding process. And we also have to deal with the key feature that we have to deal with is we have to make sure we design supports properly and figure out how to get both the supports and the powder out of the material. So what's the impact on product development of this stuff? What's kind of the things that summarizing what we just talked about? Well, key thing to remember is we've got fewer constraints, but we've got some new constraints. So it's not a panacea. For lower volume, tough problems, it's an ideal solution. We keep seeing fantastic applications for this technology. It's a combination of better polymer materials and accurate metal that have made this something that we can do. This technology has been around for a very long time for prototyping, but when we talk about making tooling or final parts that are actually going to go out in the field, it's really better polymer materials and accurate metal that have made this something that we're looking at seriously now. And I mentioned tooling. When we talk about making end-use parts, the majority right now are tools. They're not necessarily going to go out in the field. One of the reasons is you don't make a lot of tools, so it's low volume. And we can save a lot of time and money by using additive manufacturing. And we get these crazy shapes that we couldn't make any other way as well. So it's pretty cool. But we are starting to see more and more people do end-use parts. So what's the worrisome issue? The thing that should keep you up at night if you're going to try this is how do you make sure your parts are good? We got away from a lot of testing because we can use simulation and similarity with existing parts to say, oh, this is going to work. We don't have a problem here. You're going to have to go back to kind of the earlier days of some of these other methods and materials to test and do more advanced simulation to make sure that the parts are good. So before I move on to the next section, I want to do two takeaways. One's kind of a summary of what we just talked about, and the other is something we haven't talked about yet, which is the key impact of additive manufacturing on design. And this shape freedom is why we're here. Is I can make any part, any shape I want, pretty much. All these constraints of traditional manufacturing have been removed. That's the key thing to remember. And the other we haven't talked about is kind of the whole reason why additive manufacturing is a big deal. Not even when we're talking about creating these free shapes, these crazy shapes that I can't make in traditional methods. The other advantage of freeform manufacturing is I don't have to be a manufacturing expert. I don't have to have a bunch of manufacturing tools to make my parts. I can just have a 3D printer, an additive manufacturing machine, and I just know how to use that. I don't have to be a machinist. I don't have to be a metallurgist. I don't have to be a casting expert, an injection molding expert. I can make my parts myself. And we have a customer that deals with very old hardware, and they're replacing that hardware as it's wearing out. And instead of going out to 10 or 15 different shops and getting quotes and working with them on the constraints of their manufacturing methods, they're looking at using this freeform fabrication to recreate these parts themselves in their own group, where they don't even have to use internally to their company. They don't have to use the machine shop. So it's pretty exciting stuff. So that's the first section here. So let's switch gears from the idea of how we're going to make these crazy freeform parts to how we're going to design them and how we're going to use simulation to do that. Really, the only way to do it. So we're gonna take a look at some old methods. Basically, we're going to take a look at something called topological optimization. And it was big in automotive and aerospace for I think over 20 years. I think I remember using it probably 25 years ago. And it's quite common in these kind of stamped sheet metal parts like this, where you get these lightning holes. And if you've ever looked at like structures on rockets and airplanes, they'll have these big lightning holes in a wing or something. And that was kind of how they figured it out, was to lighten up those wings and those suspensions in cars. But it was constrained by manufacturing methods. The reality was that we could make lightning holes and in these machined and metal parts, but that was about it. And then outside of aerospace and these automotive structure or automotive and aerospace structures groups, people tried it, but they'd come up with something and they had no way to make it. That was always the problem. We would come up with these crazy shapes and we're like, well, I can't manufacture this, so go back to the drawing board. So that's why I put an exclamation point here, is that we need a way to make these things, and that's where additive manufacturing comes in, right? So parametric optimization was really a more useful tool, and that's what we ended up doing. So we could keep our manufacturing constraints kind of nailed down for traditional manufacturing and come up with the best shape that way. Like I said, we can use additive manufacturing to remove these constraints. That's the great thing. And when we got metal that worked and plastic, that the properties that we liked, um, these vendors that make this topological optimization tools started to dust off these older tools. It was, the people that worked in the automotive space that sold tools to Detroit and Germany and Japan that had been doing topological for some time. They kind of have a head start on this sort of thing. Those kind of niche suppliers are kind of a little bit ahead of the game right now. Maybe ANSYS is catching up a little bit or kind of matching them right now. But when we started looking at this, they were definitely ahead. And these people that make these third-party niche tools that kind of bolt on to programs like ANSYS, they started getting phone calls outside of Detroit saying, or outside of Los Angeles saying, "Hey, I want to make a part for my medical device, and I want to use topological optimization because I can now make it with a 3D printer, additive manufacturing machine." So let's back up a little bit and talk about what is topological optimization. Shouldn't assume that everybody knows what it is, even though it's been around for a while. So it's a free-form determination of where you do and don't need material. So you basically take a block of material, right? And then you apply loads. This one, very basic. You hold it here, you push on it here, and hold it down here in the corners. And you run a simulation, and it removes, adds, or moves geometry. Depends on what algorithm you're using. This most typical one just kind of removes material until you meet your goals. So for structural, those goals may be, meeting a strength goal, a weight. Maybe you're going to, maybe another thing is modes, right? You can actually say, I want to avoid certain natural frequencies. And you may want to use certain materials or minimize the amount of material you're using because it's really expensive. That may be more important than strength. And then cost also. So all these different parameters you can put into the code, and it'll, remove, add, and move material to get what you want. On the fluid side, we can use this technology on the fluid side. We may want to get rid of turbulence, or we may want to induce turbulence. That's a parameter that we can say I want to minimize or maximize. We may be looking for a certain pressure, maybe a pressure rise across a pump. We want to look at mixing of different species. We want to look at the velocity, and then again, weight, material, and cost also get into there with fluids parts. One of the best examples of this is, say, a wing on the back of a race car, right? You want to maximize the downforce and minimize the drag. I should put drag in here, I guess. I'm a structures guy. So there's two basic ways to achieve this. You can either move the surface, which is what they do usually in the fluid side of things. And the other is, on the structural side, what we usually do is we just change the material properties in this block. We have this block, and we just kind of change the material properties of an element or a cell to make it go away. That's basically what we do. So the simulation tool today, basically everybody out there, ANSYS included, is looking at improving the algorithms that they have. So we kind of had these aerospace automotive tools, and now everybody's going, I want to use it in all these other places, and I want it to work really well with additive. So we're kind of developing algorithms and processes around that. But we still have some really good tools today that you can use to do this right now out of the box. One thing to be aware of is the process is linear by nature, so you can't run multiple cases at one time like you can with standard optimization. ANSYS Fluid has something called the adjoint solver, which moves surfaces to meet certain criteria. And we have a third-party tool that we recommend called Tosca for fluids, and it kind of does the same thing a little bit differently. They each has their advantage and disadvantage. So if you want to work with fluids, let us know, and we'll help you decide which one's the best one for you. And then the ANSYS mechanical side, we're familiar with two really good third-party tools that integrate with Workbench for structural. And we use one of those. They're virtual physics. I don't know how to say it. It's physics or physics, Pixis, and then GSAM for VR and D. This is the one we use is GSAM and GTAM, which is kind of a designer version of it, and they're really, really nice tools. The nice thing is they don't use their own solvers like some other tools out there. They actually go into ANSYS, solve in ANSYS, and then use their algorithms to figure out where to remove material or add material. The other thing to be aware of, if you have your own product or another third-party product you want to use that's your favorite, is that these ANSYS products are completely open. So you can use your own tool. You can do it on a scripting level. You don't even have to get into the core of the code. You can drive a solve, get the results out, interpret them, change the geometry, repeat. It's actually fairly easy to do both on the fluids and solid side, or structural side. And then ANSYS Mechanical and ANSYS Fluid are totally open. A lot of people don't know that. You can get in there and actually get into there's user routines that you can use to go in and get whatever you want and change whatever you want. So it's very, very open tools. Um, there's other tools out there. We looked at a lot of them. We've been in competitive benchmarks with some of them. And what we generally find is that although they may have greater user base and be very good in this kind of traditional where do I put my lightning hole type of a thing, they lack the breadth and depth in the underlying solvers. They're basic structures tools. So we really recommend going with these third-party tools and then using ANSYS products as your solver. So you get the advantages of the ANSYS world along with kind of best-in-class topological optimization tools while ANSYS works on the algorithms. And we'll talk about what ANSYS is doing in a little bit. So one of the first things you need to do is make sure you get a good material model. So you're gonna go down this road and you're gonna do topological optimization, and these aren't standard parts. You gotta have a good material model. Let's talk about polymers first. It's layered. So what we recommend is that you use composites, either solid or shell composites in ANSYS, and then build one layer at a time, just like you would for the part out there in the real world. Estimate the orthotropic properties per layer based on the test data. That's kind of the way to go. This is kind of the most common method. Is we'll go out and test some samples of the material and the build method we're going to use, and we'll come up with kind of some ballpark orthotropic properties that we can then apply to each layer in my model. Now, a more sophisticated method that people are trying to look at academically and are getting further along with is actually knowing how the part was built. If I know like how my plastic was extruded in an FDM, or what the density of dots are with a polyjet, I can actually construct a per layer model based upon that, using sophisticated methodologies. That's pretty cool, and we're hoping that'll get better and better as time goes by. On the metal side, again, this also uses layers though. But on the metal side, the big issue is not so much the layers. And I'm really not talking about using binders. That's something that because you're going to be firing those parts and post-processing them, so it's kind of a different approach. You need to treat them as a sintered part at that point. But when I'm talking about direct laser melting, the big issue is residual stresses. Now, most of the better machines actually monitor what the temperature is in the build volume as it's being built, and you can use that to kind of get an idea of how hot a given layer was as the part is being built, and you can apply that to your FEA model, figure out what those residuals are. And there's this niche tool called 3D Sim. We've heard things about it, good and bad. I actually never think nothing bad. It's just it's a new tool, so hasn't been put through all the tests I think that it needs to so far. But it uses a different approach than FEA to model the build process and calculate what the thermal stresses are going to be, and then you can export those and put those on your ANSYS model, which is pretty cool. The other thing to be aware of on a material model standpoint is we're not really sure how to deal with fatigue in these metal parts that are being made using these processes. So that's something that's being researched. So the other thing to be aware of when you're talking about these tools is if you have preteens or teens that play Minecraft, you know that the Minecraft guys are all these kind of blocky looking objects. Well, that's kind of what they look like when they come out of your topological optimizer. This is a good example here. You kind of get these funny shapes, these kind of blocky looking guys, and they need to be cleaned up. And when we use a wrapper to do that, we actually use Space Claim, and I'll talk about that a little bit more. So you kind of shrink wrap it, right? You get rid of all those bumps and crevices and square corners by shrink wrapping it. And the tools are getting, when we first started using it, if you remember that red block, you kind of saw even blockier looking parts. As time goes by, they're producing smoother surfaces just out of the algorithm, but you still have to do the shrink wrapping. The other thing you got to do is, so you've got to find an element model that's the shape that the program is predicting, and you got to turn that into something that you want to manufacture. And so you got to convert facets to surfaces, or sketch and drag on the faceted geometry to create the geometry you want. So you need a tool that can do that. We'll talk about how we do it here in a little bit. The critical surfaces and interfaces need to be defined properly also. That's something that a lot of people forget, is that, I don't know if you can see on this small picture, but you got these holes here, these mounting holes for this bracket. Well, those have to be really precise. The topological optimizer may come up with an oval there, or they may come up with a surface that's not flat. And if it's an interface, you need to make sure they are. So you need a tool that will basically do traditional CAD on those areas you care about. Once you're done and you say, well, this is the part I want to make with Freeform Fabrication, you got to go model it again. You got to put it back into ANSYS and figure out whether it's going to be exactly what you want. The other thing to be aware of that a lot of people forget is tolerancing. You kind of, when you're in a new methodology with this freeform, you kind of forget that tolerances still matter. They may not matter on these crazy surfaces you're creating, but all your interfaces need to be toleranced, and maybe your overall length needs to be toleranced. So you're still going to have machined surfaces. Now, the other thing I want to, before I move on, one of the things I want to point out is we've talked a lot about this idea that I have this freeform manufacturing method, so I can use topological optimization to come up with a freeform part. And that's what a lot of people are doing. But it's not all topological optimization. It's the primary method used out there that creates these crazy, wacky parts that you can only make with freeform. But standard optimization and good old-fashioned design engineering can still come up with parts that can only be made with additive manufacturing. I mean, I've sat in front of a CAD tool and manufactured a part that's got internal features. I didn't use any topological or anything, and it's a really nice design, and I ran it through ANSYS and got all the results I wanted, but I still couldn't make it right using traditional. So even if you're not using topological, you still have the advantages of additive manufacturing. And simulation still drives the process. It's not any different. You're just using different simulation. You're not just not using the topological tool. And of course, ANSYS is an even more powerful tool for this because you've got your full multiphysics, you've got your other physics. You can optimize the part for, I don't know, an RF horn for high frequency electromagnetics. And the only way to make it is additive manufacturing, even though you've not done topological optimization on it. You can use traditional parametric optimization, which of course ANSYS rocks at and has other third-party tools that are really good at. And then space claim is just the big advantage there. Even though you're not doing topological, you still, anytime you're tweaking geometry and making complicated geometry and optimizing the design, space claim is the tool for that. So as we've helped customers do this, as we've done our own research for our own internal projects, we've had some key lessons learned. There's a lot of tools out there that have these simplified kind of designer level user interfaces, and they're really easy to implement. You can just roll them out to your engineers, but they have limited capability. You just need to be aware of that. And I'm not just saying the competition is evil because they're designer based. We recommend a tool that works with ANSYS that's designer based. You just have to make sure you use it right. And the way we recommend you use it is to come up with design ideas. What's the basic kind of generic shape? I'm not gonna use what it comes out with, but at least it'll tell me what direction to head. And it's a very quick way to do it. You can just kind of crank it out and say, oh, this is kind of a cool looking shape. I kind of see what it's doing here. I'm gonna work with this, but I'm gonna go in and maybe parametrically constrain it and do standard parametric optimization to get my ideal shape using the ANSYS tools. The other thing that we've learned is you've got to capture and include constraints for manufacturing methods available. Now, if you're using freeform, there's a lot less, so there aren't too many of these. But do remember that you have to deal with those interfaces that you have to machine. And we've seen that before, where people will make a part and they don't constrain those interfaces, and then they build it, and then it doesn't fit together. The other thing is include as many load cases as possible. So if you optimize for one load case, it may crumple when you put in some minor location you can think about. Like maybe you've got a compressive load on your structure, and you've optimized it, and it's gorgeous and it's beautiful, and you took out half the weight, and everybody's happy, and you're about to get the corporate award for most innovative design for the year, and then somebody puts a torque load on it during some kind of unusual behavior, and the thing crumples like a potato chip. So be aware of all your loads and make sure you apply them. You won't get the award if that happens. And I keep talking about this because we see it over and over again, is clearly define and lock down those interfaces. Make sure you have those, you know what your interfaces are to other parts in your assembly, and that you've controlled those and constrained those. Um, Also, and when I say results here, I mean the geometry results from topological optimization. Make sure you've got a tool like SpaceClaim that can actually deal with them. It's another thing that we've seen people fail with is that they may have a competitive product that's a decent topological optimizer, but they're trying to use their standard history-based CAD tool to deal with the results, and it's kind of a pain in the butt. You want something like SpaceClaim that's not history based and that also works with facets. And we'll talk about that when I talk about SpaceClaim a little bit more. But your traditional CAD tool may not be the best to deal with the results of topological optimization. So let's talk about where ANSYS is going in the near term here in this area. So they're going to reboot and keep going. Like usual with ANSYS, they're not going to leave you high and dry. They're not going to go off on some science project for 3 years and say hold off and wait until we're done. We promise it'll be the best in the world. They're going to do that research and development project, and they're going to release as they go. But they're also going to give you solutions that you can use today. So I went into our library and found this ANSYS manual from way back when, and the old topological optimization was there over 15 years ago, and I had used it when it was there. It was a pretty cool tool. It wasn't used much because, to be honest with you, ANSYS was not strong on the structural side with automotive and aerospace people, right? They were using that competitive tool, which we won't name, and so a lot of the work went into to deriving that tool and working with that tool, and we didn't have a lot of users. So they put their resources in places that we had a lot of users, and they kind of let it die on the vine and eventually undocumented it and turned it off. So now they're coming back and rebuilding that capability. They're using a company out of Germany that is kind of an experts in algorithm development, especially in this area, and we're really excited about that because they're not just going and saying, well, what's everybody else using, and we'll just copy that. They're seeing what everybody else is doing and trying to make it better and approaching it from a very high-end perspective. They're also making their module for doing topological as physics independent, so it's gonna stand outside and kind of be unique, which I really kind of like. And although they're starting with structural, they're going to build it to work inside the solver itself. So even though it's independent, it's going to work directly with the ANSYS structural solver. And over time, it'll be multi-physics. And then in the meantime, because those of us that need to do this today, they're going to partner very closely with third-party vendors because it's an open tool and a tool that's kind of agnostic. They even work with competitors, and VRND, Virtual Physics, and Tosca are the two that we're familiar with. There's others out there, but those are the ones that we know and recommend. So one of the things that's unique about ANSYS's approach that we're really excited about is that they're supporting the whole process. These tools for topological optimization, not just the optimizer itself, but these other tools we're going to talk about, are integrated into the full ANSYS suite. It's not just one program or a module that sits out there, and you got to hop into the module, do your topological, and then hop back into other tools. What we already have with ANSYS that's awesome is geometry import or legacy mesh import. We've had that for a long time, and that's just ideal for dealing with this approach of doing topological optimization. So we've kind of got that for free. We also have SpaceClaim, which is a fantastic tool. And one of the reasons why SpaceClaim is so useful is that it's got this wrapper built in, and it's got cleanup tools. So I can apply the wrapper, I can go in and smooth it, I can flatten things, I can pull things. It's really nice. And I'm working with facets the whole time. I can also build geometry off the facets. I can fit surfaces to it. I can drag and remove and all your standard CAD operations, but I can use the facets as kind of a clicking point. So I can trace the facets, I can drag to them. So you have to see the demo to get it. And that's a little too technical for today's talk, but if you're interested, let us know and we'd love to show it to you. And then also, I can go ahead and start with my initial guess at the geometry, my CAD geometry, and then just modify what's changed. I can use the facets to just kind of drag my existing geometry to what's just changed because of topological optimization. And that's been the huge time saver for us, because we don't have to start from scratch and go, okay, I'm going to rebuild this model. I can just modify my existing model. And I can output both your traditional CAD NURBS, non-uniform rational B-splines, is what that stands for if you don't know. So that's an exact representation of the surface. Or I can just output facets, right? Because in freeform fabrication, we didn't really go into this. I don't need an accurate NURB surface. I just need facets. That's the geometry that the 3D printers use. So I can just go straight from a mesh to 3D print. And Space Claim deals with both. If I just can't get a NURB in there, it doesn't matter. I can just use the facets. So in our opinion, ANSYS is on the path to leapfrog other solutions. They really have some cool things, some of which we aren't even talking about yet. They're going to allow them to really move forward and as usual with a complete solution, with a robust solution, with one that's easy to use but doesn't give up on capability. All the things you come used to kind of like with the whole ANSYS tool set. So what's coming soon? Um, so in coming releases, we'll see when they come out and how they come out and what's released. We're going to have stuff in ANSYS Mechanical and ANSYS Mechanical APDL. So again, starting on the structural side. It may be beta when it comes out because the quality assurance takes a while. So they don't want to hold up. They want to get it in people's hands. You know it's beta. You shouldn't use it for production, but you can start playing with it and building processes around it. There also, we're going to start seeing some tools that work with this cellular geometry. The idea is that you model this standard cell and you do a bunch of parametric studies on it to get its properties, and then you apply that to the full model. So you kind of smear the properties across the model. It's kind of an approach we've used on the thermal side, excuse me, on the material property way, like for printed circuit boards, that we're going to now apply for using additive manufacturing to make these really cool cellular structures. The most important thing that I can say to all of you listening to this right now is if you try these tools as they come out, is please give feedback to development. This is your chance to really help steer the code in the right direction. We're very excited about that. So let's take a look at the future. So what's coming? A lot of effort and research, in and outside of ANSYS, looking at modeling the process, getting better at that, whether it's metal or plastic. Also coming up with accurate material models. We talked about that, what's there now, and you'll see new stuff coming down the pipe for that as well. Another thing you'll see more and more of is this organic stuff where they're using totally different algorithms like fractals and genetic algorithms and things like that to come up with these crazy shapes that look like trees and bones and things. And there's a lot of promise with that. Also, I'm not sure if this is new or it's here. Maybe it should belong in the it's here now. Is the idea of doing single part assemblies. I think we'll see people do more and more of that. We have a sample heat exchanger that we did that was like a 8 or 9 part assembly that's brazed. It's a real pain in the butt to make. It's brazed and bolted and welded. And because of these internal features that you can't make any other way. Well, we can build it with a metal additive manufacturing machine as one part and just machine the interfaces and save huge amounts of time and money. So look for that and look for opportunities to exploit that. Also speeding up the simulation, right? That's the normal process. Is we'll get the algorithms working, we'll give you a tool that delivers usable and actionable results, and then we'll go back and figure out how to speed it up. So we're already starting to see that. And a lot of look at parallel to do that, so we can use the high performance computing. And then also spatial variation. I'm big on this. I think this is going to be bigger than people are predicting right now, especially in the aerospace area. And there's a lot you can do by not having to have a uniform density and stiffness. And then more physics. We've talked a lot about structural, and we've talked a little bit about fluids. There's no reason why this can't be applied to high frequency electromagnetics, why it can't be applied to acoustics. There's so many other areas and other physics that are already in ANSYS that we can apply this technology. And then composites. I'm big on this as well. I think this may be one of the next steps in additive manufacturing in general. Is we're already seeing it with Stratasys with their digital material, but putting fibers and multiple materials together in a single build to get really well-defined strength. And we're going to use simulation to model and drive that. Where do I put that material? How do I put it in, and what thickness does it need to be relative to the other parts? Just like we do with traditionally made composites today with ANSYS. So that's kind of an overview of what's coming. So the question we're getting at the end here, and we're all done, and hopefully you found this useful. So what's next? What are you going to do next? And by the way, before I talk about what you're going to do next, this is a bike that Airbus did using topological optimization. It's an electric motorcycle, and it was 3D printed in metal, and you can kind of see the kind of lightning stuff it does, kind of an almost organic shape that it came up with. So bottom line is, we're here to help. We can, I think we can safely say that you're not going to find an organization other than some of the large multinational aerospace corporations that have additive manufacturing, simulation, topological optimization, a really strong understanding of CAD geometry and how to make it and work with it, as well as manufacturing. Experts in all those areas in one place that can help you. We're kind of unique there. We can look at your needs, where you are, and then get you where you want to go. That's what we do for a living, and we love this topic. We're extremely excited about it, and would love to help you get what you want to go. So contact us. Info@padtinc.com is our general email address. It doesn't just go to a sales guy. It goes to actually me usually, and a few other people, and we do triage on it and figure out who in the organization you need to talk to, and we'll pass it on to the engineer that can help you the most. Or you can email me directly at eric.miller@padtinc.com, or give us a call at 480-813-4884. I'm kind of hard to get hold of on the phone, but others here are a little bit easier to get hold of. So we hope you found this useful. We hope that all the information we put out there is useful. Let us know what you think. Let us know if you want to see more. And we hope to see all the cool things that you do with combining this idea that I can make any shape with freeform fabrication, and I can drive the design of any shape using topological optimization and other ANSYS tools to come up with new and better products that are cheaper to make and last longer and perform better. So good luck, and let us know how it goes. Thank you.